Okay, so this is the first lecture after lots of work on background and establishing some language and some perspectives on how to look at dynamics. The first section of where we actually do proper model reduction. And remember what we said at the beginning was that what type of method we use for model reduction depends on the fast dynamics in scale-separated systems. So if the fast dynamics converges to a fixed point, we're going to use one method. That's how we start. It's called manifold theory. If it relaxes to, let's say, a periodic orbit, we're going to use something like averaging. So we're going to do that today. And then later on, we can see what happens if it relaxes to a chaotic attractor, or if your fast dynamics is some stochastic process that generates some ergodic density, invariant density. Okay? So let's start with model reduction for now deterministic systems. With scale separation. The weakly coupled case we do a couple of lectures later. And let's start with the first case that the fast dynamics relaxes to a fixed point. Okay. And what we're going to learn about today is called center manifold theory. So let's say we have two variables x and y, and we have two, they're described by two ODEs, and let's say x, y are in some Rn cross Rm, and we have a linear, entirely linear part for both of them, so this is linear. And then we have some nonlinear terms, and they're entirely nonlinear. So f, did I call it f? X and y plus g x and y, and these are our nonlinear terms. And let's assume that this system here has a fixed point at 0. Okay? So, if you want to look at the stability of this fixed point, what you've done in Rama's lecture, is you looked at the eigenvalues of this matrix, right? And you said, okay, if they're all negative, you have a stable system. If there's some positive, real positive system eigenvalues, then you have instability. So the case that we're going to look at now is what happens if the real parts of the eigenvalues of this matrix A is now 0. Okay? And these are, let's say, negative. For simplicity, let's say that the real part is negative here now. So then, all the theory that you learned in Rama's lecture doesn't work anymore. Okay, we can't say anything about linear stability if the real part is 0. Okay, so what do you do then? Okay, that's the question we're addressing here. And we'll see, you see, if this is 0, and we are close to a fixed point, 0, which is at 0, 0, the real part here is 0, then this is a slow equation. There's no growth rate, nothing, whereas this one here has a fast decay rate. So this is slow and this is fast. Okay? So our aim then is to get an equation that is only for the slow variables, where we somehow have to replace y. Okay? We want a closed equation for the slow variables. Okay? So the other assumption, so we're making is now, if we look at the eigenvalues of A, and then take the real part, we want them to be 0. And we want that the real part of the eigenvalues of B is, well, less or equal to some lambda, which is strictly on the way from 0. Okay, so these have 0 real eigenvalue, and these have negative, clearly negative one. Okay? These are matrices. This is a linear part of your system. Let's say there is a linear part. Yes, so we assume that if we want that the fixed point, there's a fixed point at 0, 0, we need that f of 0, 0 is 0, and g of 0, 0 is at 0, right? Okay, so now, as a comment, we can't say anything about the stability of the fixed point 0, 0. Okay? So all those methods you learned don't work. So, yeah? No, that's what they're strictly nonlinear terms. Okay? So df at 0, 0 is 0. Okay? And dg at 0, 0 is 0. That's right. That's right. Say again? A linear what?
Linear in y. Linear in y.
Linear in y? No, that's right. We just put it in that form, yeah? There's no, that's right. So otherwise we do some coordinate transformation and bring it into that form. Yeah? You had a question? No, they're constant for now. They're constant. Okay? So in the linear case, the picture you have in the y direction, you now have, if this is my fixed point 0, 0, you have a fast contraction, that's my eigenspace. So this is a stable eigenspace associated with the y direction, and this is what's called a center space in the x direction. So here we have no idea what happens around 0. Okay? So this is the linear picture when we set f to be 0 and g to be 0. It's the entirely linear case. So the question is, how does this picture become once we switch on the nonlinearities? Okay? So what will happen is that these, if we get very close to 0, we should have something that looks, if we make this into a microscope, even in the linear case, it should look like this. In nonlinear case, it should kind of look like this. But if we go further away from the fixed point, in the x direction or in the y direction, it will look differently. So close to the fixed point, the stable manifold would look like this, but then it kind of can bend away. Okay? So it will kind of look like this. So this is now, let's call it WS. So this is when we have, now f is non-zero and g is non-zero. So nonlinearities are switched on now. So close, we become tangential to the linear eigenvector, but then we can deviate. So the interesting part is how this EC, the center space, deforms. So locally, it will be flat, but then it can kind of bend away. So let's call this WC. Okay? It's like a sheet now. Okay? It was flat, we just bend it up. Okay? I mean, it can be bent like this. It doesn't have to be, you know, it can have some structure in that direction. Okay, so what does the dynamics do? So what the dynamics does is the following. you have, if you now start, well, if I start exactly on here, these are invariant manifolds, I stay on that one. But let's say I put an initial condition, let's say this is my, here is my stable direction, and now take an initial condition from here, okay? So now I will have, go very, very fast onto this, what's called the center manifold, this blue sheet, very fast onto here, and then I have slow dynamics there. So I go boom, down here, and then on a computer you would think nothing happens, but it sort of then creeps, somehow some dynamics happen slowly on that manifold. So this is a locally invariant manifold, okay, on which I stay. Similarly, if I stay, you know, go somewhere from up down here, boom, I go very fast onto the manifold, and then some slow dynamics will happen. Okay? The Y dynamics is fast because of this. If it's a small number, it will, if it's 0.1, it will still be, this will still much faster. The contraction towards here is still much faster than the drift on this center manifold. Okay, so in some sense, the actual value here, I mean, if you put it on a computer, of course, if you have you know, if it's minus 10,000 or minus 0.1 makes a difference. But still, even with 0.1, if lambda is minus 0.1, the attraction to the center manifold will still be much faster than what will happen then on the center manifold. That's right. That's correct. You could have imaginary like oscillations around. That's right, which are much faster than this. That's correct. You can definitely have that. Yes. Yes. That's correct. Yes. Okay, so this WC here is called the center manifold. I'm going to define it properly. Our aim is, now once we are on the center manifold, we have slow dynamics. So our aim is that slow dynamics is now the dynamics restricted to that center manifold. That will be our reduced model. Okay? And we'll discuss how to do that. Once we've done that, so we will get this reduced dynamics on the center manifold, or on WC. And that will allow us to finally determine the stability of the fixed point. Okay, so that's one thing we can do with it. And another thing that we're not going to discuss, but if people if you, in your own research you come across that, and we can discuss this offline afterwards, you can use center manifold to study bifurcations. If you have a very complicated system, you know something is happening, but you don't know what bifurcation it is. Center manifold theory helps you unraveling what type of bifurcation you have. And also, here we just want to discuss ODEs, but it works for maps, it works for PDEs, and delay differential equations, and so forth. So again, I'm not going to touch PDEs, but some people of you might have similar problems there, so I'm happy to talk offline about how to apply center manifold theory in PDEs. Okay. So let's define what a center manifold is. Just a definition. So an invariant manifold is called a center manifold if if it can be described locally, and I'm going to underline locally, so everything we do here is local, close to the fixed point. Okay? So if it can be described locally, as follows. So if we can describe it locally as a graph, so that says we can write y is some h of x. So this is locally, this blue curve here is a graph. If we know x, we know the value here. Okay? So y, we can now express y as h of x. Sorry? WC. The center manifold is invariant. So that means, the dynamic stays on it. Yeah? And then I'm going to stress the local aspect. So this is for x sufficiently close to 0. 0 was our fixed point. And we want that near the fixed point here, well, we want that the 0 remains the fixed point. So we want that h of x equal to 0 is 0, because that's our fixed point y equal to 0. And we want it to be tangential to our center space at 0. Okay? So that means if we go very, very local, it looks like the linear, we approach the linear case. Okay? And that also means that down here, the dynamics is flat. It's just has only a component in the x direction. There's no projection onto the fast direction. So that means here you get rid of all the fast components. Okay? So we also say that we are tangential. So d h0 is 0. So no fast or no projection onto fast eigenspace at fixed point. Okay. Okay. And this is for sufficiently small epsilon. Right, so we can always find some kind of small region around our fixed point where this is it. So maybe I start first with stating the theorems before we see how to apply it. So there are theorems that assure in systems like this here the existence of such an invariant manifold. Okay? And in the theorem you already see how we can apply it to do model reduction. So the theorem says that the dynamics on the center manifold is locally, so that means near the fixed point, given by u dot is AU, right? So this is here, x is u, u dot is AU plus f of u, and now y is a center manifold, so y is h of u. And now we have actually a closed system for our slow variable. Okay? And y is h of x defines the center manifold WC. Okay? Let's give this equation a name here. And let's give this system is our equation 1 star. Then there's a theorem on convergence. So just because we have asymptotically, we have two systems that are kind of asymptotically close, does not tell us that solutions of this system and solutions of this system are also close. Just because something, two equations are close doesn't mean the solutions are necessarily close. So we have to show that too. well, we're not going to prove that, but I'm going to state it. So it says that the stability properties of the full system here, this n plus m dimensional system, is the same as the stability properties of this reduced n dimensional system. Okay. So the stability properties of the fixed point are the same for the full system and the reduced system. And then say we are now stable. I mean, if we're unstable, we're going to leave the linear region and we're going to leave the center manifold. Okay? So the interesting case where we can actually compare solutions is if the dynamics remains on the center manifold. So this is a stable situation. So in case of when the fixed point is stable, then for, let's say, x naught and y of time t equal to naught sufficiently close, or small, sufficiently small, so sufficiently local, x of t is equal to u of t. Well, almost. I mean, it's an approximation, but it's a damn good approximation. It's exponentially close. Okay? So the errors you're making are exponential in time. Okay? And similarly, y of t is h of u of t plus order e to the minus gamma t. Okay? So you're exponentially close. One side remark is the center manifolds, we know they exist, but when we determine them, they're not unique. Okay? But all of them are exponentially close. That's just a side remark. Okay. So let's see how we can use it. No. But it's exponentially close, so for each of those, you still get exponential closeness of the solutions. Because you can approach, you have uniqueness of your solutions, so you approach them differently. That's a good question, right? I didn't say anything about it, how we find it, right? So far, it's just existence, okay? So we have to define it. That's what we... This just tells us there is such a center manifold, but yet, how do we use it? Right? If we found it, yes, great. We found our reduced system. Okay? But we need exactly, that's the next step, how do we determine it? Okay? So, let's look.
So, since the manifold is not unique, that means there are many possible choices for match.
Yes. But they're all exponentially close.
And for so does the gamma depend on H?
Yeah. I don't know, but I doubt. I think it must somehow depend on lambda and on f and on g. So on f and on g, and maybe one can formulate that. Yeah. Oh, on which? No, I don't think so. No. But I don't know. I'm not. But I wouldn't think so. Okay, so let's take an example. What did I take? So let's take an example. Let's take x is in R. No linear term here. And y dot is minus, why do I have that? Now I make it very fast here by putting an epsilon there. I'm not sure why I do that. I don't think I need that. Hold on. Actually, yeah. Okay. So here lambda is -1, strictly bounded away from 0, which is the eigenvalue of here. This is already in diagonal form. Okay, so we know what the eigenvalues are. 0 here. So this is in the form of the systems we are looking at. Okay. So you could think, oh yeah, here we got this exponential damping here. So you could say, okay, y goes to 0. So you could say, okay, well, x dot is minus x to the 5. And then you will get that x is stable, that 0 is a stable fixed point, right? But it's wrong, right? This intuition is wrong, but we know better. We know we should actually look at the center manifold. So now your question, how do we get the center manifold? So on the center manifold, we have fast contraction towards it, and then it doesn't move. I mean, it moves very, very slowly. So it doesn't move. Since y dot is 0, roughly 0. Okay, so if y dot is roughly 0, y is x squared. Fast is bzzzt, and slow is this. Slow means linear part is 0. You see, these terms here, they're very, because this is quadratic at least in x and y, so since we're locally near 0, they're small, so the linear part dominates. Linear part here is 0, so x dot is something very small. Okay? Here, y dot is minus lambda, which is far away from 0. The lambda, right, is bounded away from 0. So that is the exponential contraction here. Okay? Yep. Where were we? Here. So now, this is an approximation to our center manifold. Okay? Now, we have expressed y as a function of x, as a graph. We can insert that into here. So now we get x dot is x to the 4, well, minus x to the 5. But since we are local, this one is higher order, right? That's much smaller than this one since we're close to 0. So now we got x dot is x4. So this is not the picture we're going to get. This is our center manifold. I should use blue. Sorry? I did not catch this, sorry. What was your question? It's okay? Okay, so this is a center manifold. So now we would, boom, go quickly down to here. We're interested in the stability now. If you ask for the stability, x dot is x to the 4. So if we start, let's say we start here, we contract quickly down here, and then we have a slow drift. So we start here, go fast, attract towards the center manifold, and then we go slowly down here and go through the fixed point. So it's not stable. Okay? So now we can determine it. I mean, one nice thing is we can determine the stability, although the real part is 0, by doing the center manifold theory. Okay? Yes. You can prove that. We didn't prove that. This one is an approximation only to the center manifold. This is not the exact center manifold, right? You can get higher and higher approximations. We do this in a minute, okay? So we know there exists something that is locally invariant. It's not invariant everywhere. And this is an approximation to it, okay? Yeah, so it's flat here, right? Now, y dot is 0. Y dot is 0 also here. On the center manifold, y dot is 0. Y doesn't, I mean, it moves down here now, but very slowly. So to an approximation, y dot is 0. Okay? So it's just an approximation, y dot is 0. Okay? We just said it. This is to the lowest order. That's correct. As soon as it hits, that's right, y dot is 0. There will be some region where it is local. Okay, so for sufficiently small epsilon. If you start far away from the fixed point, we don't know what happens. No, maybe not. Maybe, but you may not hit this maybe you don't hit this manifold here. Right? This y is x squared is only valid close to the fixed point. No, it's local. Exactly. And there is one more, right? The other one is 1. 1, 0, 0, 1? No, which one? 0, 1, 1. So there's another fixed point at 1, 1, right? So as soon as we go to 1, 1, there will be something else. So at 1, 1, we can do another center manifold, okay? Exactly. So this is just local. But how do we find it? First of all, I should kind of some lingo here. What this in some sense says here, the existence of a center manifold, is that the fast dynamics, the y dynamics, is what's called slaved to the slow dynamics. Right? The slow dynamics does something, so you got some dynamics in here, and the y just follows through this algebraic relation that y is h of x. Okay? So y is h of x, so this is the existence of a center manifold. Some people say that y is slaved to the slow dynamics. And some people call it the slaving principle. So Hermann Haken, who was a physicist, he called this the slaving principle. But it is center manifold, and the mathematicians were actually a little bit earlier, I think, than the physicists. It's one of the few instances. Okay. So how do we construct it? This is just lowest order. What I didn't write here, but is that the center manifold here, this WC, is smooth. It's locally very smooth. So if it's smooth, that means locally we can approximate it by a polynomial. Okay, and we're going to use that to construct the center manifold to higher orders. Yes, please. Yeah, I mean, eventually it will change, but it will only change through x, right? Of course it will change, right? You're not going to stay here. It is almost zero. It's compared to the dynamics on x, compared to the dynamics of this variable here, it is 0. No, will not go finally to 0. Oh, yeah, but then you say that this is a stable fixed point if you finally go down there. But in this instance here, the fixed point is not stable. You're not going to go to 0, 0. You will go up to here, and then you will be ejected. Like then at some stage, you move along here, and then you will leave that manifold because you leave the local region. Okay, the fixed point here is unstable. Yeah. Sorry? Yeah. So what do you want to do? You want to look at level sets of y dot is equal to 0, but they are only this is only approximate, right? So no, it's not exactly 0. It's just 0. It's just very small. It's small compared to the dynamics on the slow manifold. Okay, it's not 0. So I'll show you why it's not 0 if we do this. Maybe it becomes clearer when we just say, okay, let's look for better approximation. And all we're going to use is that the center manifold, this h of x, is smooth near the origin, so we can expand it as a power series, okay, in terms of x and y. So let's do that now. This we don't need. So how do we construct the center manifold? Well, we said at lowest order, we just set y dot equal to 0, so there's no fast time dependency at all. Just say that. But at higher order, well, we have given two pieces of information. We know that y is h of a. So we know that y dot was, I have to rewrite my system. So x dot was ax plus f of xy, and y dot was bx, and well, let's make this 0, bx plus g of xy. So y, on the one hand, y dot is now by, which is h of x, okay, plus g of x, y, and y is h of x. And also y dot is just dh x dot. So this is dh, and then x dot is ax plus f of xy, and for y I substituted the manifold h of x. Okay. So now we have a quasi-linear equation for h. So dh ax plus f of x h of x equal to bh plus g of x and h. So this is now an equation, quasi-linear PDE for h. No one wants to solve this. This is far too complicated. So let's do it approximately. And approximately, again, uses that locally we have a smooth manifold. So let's make an expansion of h. Okay. So we look at an approximation. So the approximation is that, well, assumption is h of x is smooth near the fixed point. Okay. So that means we can approximate h of x locally as a polynomial. Okay. So if you want to write, so what we want is our h. So we want to have it as a, a naught. Well, let's write a naught plus a1x plus a2x squared plus a3x cubed and so forth. Okay. I made a mistake here. I made two mistakes. Right? This term here has to be 0. Because at the fixed point, if 0, 0 is a fixed point, that has to be 0. I made one more mistake, because we want it to be tangential. Okay? So this term here also has to be 0 at the fixed point. Okay? Because otherwise I have at 0, the derivative would be a1, so it has to be 0, so a1 is 0. Okay? So let's take an example. Let's take this example here and push it to higher order. Okay? I mean, just for fun, we're not going to learn much from that except how to use the method. We're not going to learn more about the system here because we basically learned everything about the system we can possibly ask, which is we determine the stability. But just for the heck of it, let's try and push it to higher order and see how the machinery works. Okay? I mean, normally if you would do if someone gives you that problem, you would stop here at that order already, because you can determine the stability. Okay? But if you really want to know the solution better, a better approximation of the center manifold, for example, if you're more interested in accuracy, you can push it also to a higher order. Okay? So let's try this. Are we? So we had x dot is x squared y. I'm going to do this fast, but you can verify this. So this was our system. Now y is, I'm going to use a naught because otherwise I wrote it like this. Otherwise I'm going to make mistakes. So this is not this a naught here. I just shift the index. I need a3. Okay, so now we do the same thing again. We know y dot is dh dx times x dot, and so dh dx is 2a naught x plus 3a1 x cubed plus higher order terms. Maybe we need my next one more, plus 4a2 x, what? X squared, x3, times an x dot, so this is x squared, times, now comes a naught x squared plus a1 x cubed, and minus x to the 5. Okay? And similarly, y dot is given as minus y, so minus h, so minus a naught x squared, minus a1 x cubed, minus a2 x4, minus a3 x5, minus blah, 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 plus x squared. Okay? And now we're doing asymptotics. So x is small. So x squared is bigger than x cubed is bigger than x4, and so forth. So the lowest order, so we're doing asymptotics or epsilontics. So we look at the highest order. The highest order is a quadratic order. So it's x squared. So at order x squared, there's no order x squared. Oh, there's no order x squared in here. There's only an order x squared in the y dot equation. So if you want to kill the order x squared term, we have to choose a naught to be 1. So minus a naught x squared plus x squared equal to 0. So a naught is 1. This is the lowest order. It's what we had here already. Okay? It's just the lowest order. Next order, x cubed. Where do we have an x cubed? We have an x cubed here. Here, it's 5. The fifth order is the x to the 5 is the lowest. So this term and this term, they have no other term to balance. So a1 and a2 have to be 0. So a1 x3 equal to 0 and a2 x4 equal to 0. So a1 is 0 and a2 is 0. Okay. So now at order x to the 5, we get our first non-trivial correction to the lowest order approximation. So where are the fifth order terms? Well, there is one here. And what's fifth order? It's a combination of x to the 4 with x. And that's it. Oh, and there's one here, minus x to the 5. So we have 2 a naught squared minus 1 x to the 5. Correct? No? No, that minus 5 doesn't, because that would multiply this one, right? Correct. That one doesn't. So it's just the 2a naught squared x to the 5, right? It's just this one. And that is equal to minus a3 x to the 5. So a3 is minus 2a naught squared. A naught was 1. What? Minus 1. Minus 2. Yeah? So now y is x squared minus 2 x to the 5 plus higher order terms. You can go further and further and further. Okay? All right. So this is just to show you how it works. Okay? Now, a remark. We want to go to stochasticity, and I just talked to someone who's using a method called HMM for heterogeneous multiscale methods. So the following might be interesting to you. Let's see when we now have some randomness in our initial conditions. So assume that stochasticity enters again through initial conditions. Initial data. So from center manifold theory, we know that rho naught, this initial condition, t equal to 0, will converge, right? This is some kind of, lots of, like a cloud of points. All those points go down to the center manifold and then evolve on the center manifold. So this one will evolve into rho of x, y, and t. Well, let's just write it in our fancy way here. Okay, so that's propagated by the Frobenius-Perron operator on the initial data. And center manifold theory tells us this. So this is where center manifold theory comes in. That this will evolve into delta y minus h of x. And then we have some kind of rho hat that only depends on x and t. Okay. So also for the density, we can now find a reduced equation. Okay, so reduced Fokker-Planck equation, reduced Liouville equation in this instance. Sorry, Liouville equation. Okay, so where rho hat xt solves the Liouville equation associated with the reduced dynamics. So you see this as a density, your right-hand side, you can kind of understand as an average over this density here as well. So that's what you can use in heterogeneous, heterogeneous multiscale methods, right? You're trying, with the fast microsolver, you're trying to estimate this density here. Yeah? Okay. Right. So this is what I wanted to say about center manifold theory. 8 minutes, perfect. So now we kind of know what to do in deterministic systems if the fast dynamics relaxes to fixed point. And again, fixed point means y is h of x because x is slow, so x is constant. For each y, if you're y, for you x is constant, so you're converging to a fixed point. Okay? But let's see what happens if now we converge to, if the y converges, the fast dynamics converges to a periodic orbit, and then we use averaging. So B, y converges to a periodic orbit. So we consider now a dynamical system where we have dx dt is f of xy. So again, x is n-dimensional, and we have an m-dimensional y that evolves fast, so epsilon is small. So this is now fast time evolution here, g of xy. So fast and slow. And we assume now that we converge to some, but let's assume that we converge to some ergodic, that the y dynamics is ergodic. Okay, so we have a delta measure on a, let's say, periodic orbit, we have a delta measure on the periodic orbit. And now what you can do is you treat x as a fixed parameter. So it's the same philosophy as for center manifold theory in the fast dynamics. Okay. So that means here you generate a measure, an invariant measure, that's conditioned on x, which is considered to be slow. Fixed, sorry. It's so slow that for all practical purposes it's fixed. Okay? I mean, that's also what you use in the heterogeneous multiscale method, right? You kind of, in one version, you just fix your slow dynamics. So let's say this is now the unique invariant ergodic, lots of words say the same thing here, measure that's induced by the fast dynamics. Okay. Then what you can prove that on timescales of order 1, you can now average the slow equation over the measure induced by the fast dynamics. Okay? So you can show that the average system dx dt of f of x, where f of x is now the average of the slow vector field over this measure induced by the fast dynamics. Okay? And this, or solutions of this equation approximate. Sorry? Oh, sorry, yeah. And solutions of this averaged deterministic, this average system, approximate solutions of the full system, okay, on timescales of order 1. Okay. A remark here. So let's make a connection to center manifold theory. So in center manifold theory, this mu x dy is delta of y minus h of x. Okay, dy. So f of x would be integral of f of x y delta of y minus h of x dy, which is just f of x h of x. So you can express this center manifold theory as an average. And again, this is what you use in your numerical method, right? Also, in some form. Okay. So I think just one example of this, and then we can go and get stochastic. No, the slow is unique as well. Then, I mean, the only time you can lose. Okay, there's one. Careful. No, there's an issue here, right? There's a very subtle issue. So, if this one would not depend on x, so if this would be a skew product system, right? Then I'm not conditioning on x here. And if this is now uniquely, if this is now ergodic, then I just average over the measure, and this, I have a very nice vector field here. So, but we couple back here. Okay, this is an important, thank you, this is an important point. So let's imagine that while my x is like a slope parameter. So let's imagine that, you have all these kind of, attractors or fixed points here, or whatever, or limit cycles, whatever you want. And let's say you cycle through and the measure doesn't change smoothly with your x. So let's say for x is 0.1, you have a limit cycle like this, and then for x is 0.1 plus 10 to the minus 10, you suddenly have a very different limit cycle. Okay, that means your measure doesn't change smoothly within. So that means your average vector field here is not going to be Lipschitz anymore. Okay, so you don't have uniqueness of your solution anymore. So I'm not going to go into this. This would go into linear response theory and things like that. So I'm happy to talk offline about this. So what we're assuming is always dynamics here obeys linear response somehow. So if that means anything to you. Okay, but it's an issue. So the back coupling here, this one here, is an issue. Okay, and that's not satisfactorily solved in the community. Okay, so thanks for that. Yeah. Okay, so let's take a simple example. Again, just to see how this all works. So x dot is mu plus q squared x minus x cubed. And now we have a linear oscillator q dot p dot. So q dot is p, and q dot is not, a p dot is not just minus q, but the frequency depends on x. So this is now, we have a fast. You see that qp, q of t, is just some a cosine omega t plus b sine omega t, and omega is just x squared over, x over epsilon, and a is initial condition, b is q dot of naught over omega. So we can solve this as a linear oscillator as a function, so where we treat x as a parameter. Because epsilon, you see the frequency, epsilon is small, so we have very high frequency. So this is fast, right? So QP is fast, and now we want to average this over the measure induced by this fast dynamics. Yes? Sorry, I didn't catch that. So this is a connection with the center manifold. So this would be your center manifold. I look at systems where we have a center manifold to show you that you can express that, the center manifold kind of framework theory where we say f of x and then we replace y by h of x. You can also understand as an average over this measure. Yes. Averaging is just a framework. It just doesn't, it's not only working for periodic. We're going to use it later on for chaotic dynamics. We're going to use it for stochastic dynamics. All you need is some ergodic, some measure, right? Some invariant measure. Sorry, I didn't hear you. This is center manifold. I just re-expressed it differently. No, this is not center manifold. This is averaging. This is a very different, uses very different techniques to prove this. It's just to make a connection. There are systems you can solve with averaging that you can't solve with center manifold theory. Okay? But you can always express center manifold theory in this averaging framework. Yeah, I don't want to get too technical with subsets and here things. Just no, you wouldn't. You see, this doesn't tell you how you get the h of x, right? This averaging here, this thing doesn't, we just use the existence of some h of x, but it doesn't tell you how you get it, right? This is really just kind of to see, okay, can we relate those things, kind of to give a bit of relations between the things. I thought this was helpful. Yes? Averaging is much more general. I'm just saying that you can, the center manifold for this fixed point that we defined, you can also express in this way in the averaging framework. This one here, you mean? Yes. Yes. Yeah. So this would be the vector field.
The dynamics of x, the solutions of the capital X.
They're close. So the supremum in the supremum norm x, for fixed t, small x of t minus capital X of t, goes to is bounded by something, epsilon. Okay. Okay. So now we need to calculate what is x dot, the integral f of x q mu x dq. Well, we now have our periodic orbit here. So the measure is now the measure concentrated on this periodic orbit. Okay. So how can we parameterize the periodic orbit? If we go once around here, well, by the angle and so by the time. So we can just integrate this or we can understand this as this is not a time average, right? This is just expressing this measure here on the circle and parameterizing the circle by time, right? One oscillation by time. So this would be 1 over the period, which is now x over 2 pi epsilon times 0 to 2 pi epsilon over x. And now we have f of xq dt. We parameterize with t. And so this gives me, I can't write this, so I'm writing it here. So we're going to get that x dot is mu plus a squared plus b squared over 2 times x minus x cubed. So the effect of the fast variables here is to shift this parameter mu. Okay? And we already discussed a system like here that had, fixed point 0, minus 1, and plus 1, or whatever. This is now, this is square root of mu plus q squared. So this one will here, this one delays kind of or changes when the bifurcation happens and where, into what asymptotic state you go. Okay, so that's the effect, the averaged effect of the fast dynamics. In this instance, yes. Yeah. But you can have delayed bifurcation, so it could be stabilizing as well. It's not a general statement. What? This measure here, now I say, well, okay, that's the... Sorry? What is h of x? Okay. You've never seen this. You've never seen this in your life. I liked it. Okay, so this is, now we become stochastic. Now tomorrow we do averaging again, but we use a different framework, and that allows us to treat stochastic systems and do perturbation theory. Okay? And kind of evaluate things to certain order. Okay.